Confidence intervals for proportions. I'm actually going to use a lot of voting examples with this. It seems relevant given that we're right about Election Day here. Actually, this video is being recorded and posted on Election Day. So a common thing around election time, when you're watching the news, they'll talk about, a poll was conducted and they found that, say, 52% of people surveyed plan to vote for a particular candidate. And sometimes they'll say, like, underneath that, a margin of error of like 2 to 3% or something like that. The idea is that they're using the sample and getting a proportion from the sample. Out of however many people they surveyed, 52% were found to give a certain response. And the idea is then that they're trying to apply the results of the survey to the entire population of all registered voters. So, much like when we use the sample mean to estimate the population mean, we're going to be using the sample proportion to estimate the proportion of the full population with, again, some margin of error. So we're going to be constructing a confidence interval in a similar fashion to what we've done so far for both for the mean for both large and small samples. So there's a few things that we need to establish first. When we are talking about a proportion, we're typically talking about one result. There might be, again, if we're talking about who you're going to vote for, there might be 10 different candidates, but when they're calculating the confidence interval, they calculate it from the point of view of a single response. What that means is that they're treating it as binomial. Did you give the response we're looking for, or did you give literally anything else? So it's, yes, I gave what I'm looking for. No, the person did not give what I was looking for. So the idea is then that what we're actually looking at with a proportion like that is that we're looking at an underlying binomial distribution with the random variable x where, so this is a binomial distribution with n trials. That means that is the sample size. That is how many times the question was asked or how many people we surveyed. And a probability of success P. Those are the parameters for a binomial distribution. Now, the idea is that x then represents the number of successes out of our n trials. So what we get then is that our proportion of success is p hat, or sometimes written p prime. If you happen to look in our textbook, they use p prime, but p hat is a very commonly used notation as well. And it is equal to the number of successes over the number of trials. Now, with that in mind, there is a rule for binomial distributions and for finding probabilities in a binomial distribution. When n is large enough, and p is not too small or too large, the binomial distribution X is X has a distribution, a binomial distribution with parameters n and p. The binomial distribution can be approximated by a normal distribution. Where the normal distribution has parameters of the mean and the standard deviation of the binomial distribution. Now, what does that mean when n is large enough? How large is large enough? And what does that mean when we say p is not too close to 0 or 1? Those requirements are typically settled by this, that n times p is greater than or equal to 5, and n times 1 minus p is greater than or equal to 5. 1 minus p is also known as q. The idea is that if we have a very small sample size, n, like if n is only 7, then we're going to have a very hard time making sure that our n times p product is bigger than 5 at the same time that our n times q product is bigger than 5. So what we need is a fairly large n value. Certainly if, say, n was 100, it's a lot easier to make sure n times p is greater than or equal to 5. In fact, if n is 100, p would have to be smaller than 0.05 in order to fail that requirement. Or going the other way, 1 minus p, which is q, that's the probability of failure. If p is incredibly large, then q is incredibly small. And that's kind of the idea, is that if p is very, very small, q is large, and if p is very large, then q is small. So we want to make sure that we're not skewed too far in either direction. And that's what these requirements are about. So as long as n is large enough, in conjunction with p not being too far to one side or the other, and usually all we need is a pretty large sample size, and we've got this covered. In that case, then we can use a normal distribution, which has parameters mean, n times p, and standard deviation, square root of n times p times q. Excuse me. Now, how does this actually work? What we've got at the moment is that x is represented by the normal distribution with parameters np and square root npq. Now, we're close here because remember, we said before that p hat is equal to x over n. So what I'm going to do here is I'm going to introduce a division by n to each of these parameters, the random variable and the mean and standard deviation. A little bit of algebra then will turn this into p hat, x over n is p hat, has a normal distribution whose mean is the population proportion. And with a little bit of algebra here, we get pq over n underneath the square root. So what does this all mean for us? Well, the big takeaway from this is that it means that in order to use a sample proportion to estimate a population proportion, we get to use the normal distribution, which means we get to use z-scores. So our margin of error is going to be our z sub alpha over 2 times the square root of p hat times q hat over n. Where, remember, that q, or in this case q hat, is equal to 1 minus p hat. So we're going to be using the normal distribution, which is great. Much like the mean, the confidence interval for the mean with large samples, we get to use the normal distribution. So none of that funky t distribution stuff, just a normal distribution here. And the other values, n, the sample size, and p hat, and from that we can get q hat, are given to us in a problem. Let's take a look at an example here. So suppose for a class project, a political science student at a university wants to estimate the percent of students who are registered voters. They survey 500 students and find that 300 are registered voters. So let's immediately start with this. Our sample size is 500. We surveyed 500 students. We found that 300 are registered voters. 300 is the number of successes. 300 is the number of successes in our 500 surveyed people. So that means that our sample proportion is the number of successes over the sample size. Now, by extension from that, we can find q hat as well. The idea is that p hat and q hat should always equal 1 because p is the number of successes and q hat is the number of failures, the number, the percentage rather of failures. Now, we are told then to determine a 90% confidence interval. So that's our confidence level, which then gives us alpha. And from that, alpha over 2 is 0.05. So once again, we're looking at a normal distribution here, a bell-shaped curve that's going to have 90% of the area in the middle with 5% to each side. And what we're looking for is the z-score either one of these. We can either do the z-score of with 0.05 of the area to the left of it, or the z-score with 0.95 to the left of it. Ultimately, they are the same z-score because this distribution is, again, symmetric, but one is positive and one is negative. And that we can get from the calculator or a z-distribution table. We need the inverse normal command. Now again, we're working with the normal distribution, not with a t-distribution. We need the inverse normal command with 0.95 area to the left. And that gives us 1.645. 3 decimal places is appropriate. And now we have all the pieces we need. The error-bound margin, the margin of error here, then is our z-score, 1.645, times the square root of p hat times q hat over n. Now remember, the denominator of 500 is underneath the radical, so be careful when you're typing that in. But again, we can put this all into our calculator at once if we put it in carefully enough. And what we get out of it is 0.036. Like any other confidence interval then, the idea is that we take our point estimate, which is p hat, and subtract the margin of error e and add the margin of error e. So our point estimate is 0.60. That's p hat. 0.60 minus 0.036 and 0.60 plus 0.036. And what we get at the end of this is 0.564, comma, 0.636. So what this means is that at the 90% confidence level, we can be 90% confident that the actual proportion of students who are registered voters at this university is between 56.4 and 63.6%. Now, what you typically will find with proportions is that we tend to have a little bit wider of a confidence interval. Now, again, this was a 90% confidence level, but there is a bit of a tendency to have maybe a little bit larger, just a little bit larger margin of error here than you will typically see for the mean. But the mechanics of it are still the same. It's a slightly different formula for the margin of error E, but we are once again using the normal distribution. So that's a nice plus. We don't have to worry about degrees of freedom or any of that stuff. We just get to use the normal distribution. But again, if we're using a calculator, then really the difference between the normal distribution and the degrees of freedom is just, and the t-distribution is just what is it you actually have to type in the calculator. Now, we didn't worry about this with the previous lesson where we did the confidence intervals for the mean for small samples, because the idea of the small samples was that we weren't worried about hitting a certain margin of error. We were concerned with the fact that we had a small sample to begin with. But if we go back to when we had large samples and we were estimating the mean, we had a situation where we could say, well, if I want to have a particular margin of error, how large of a sample size do I need? We can see that again here because, again, we're not looking at a constriction of having a small sample size, being in a situation where I am working with small samples. We're now allowed to use samples as large as we want. So the idea here is that we can take the formula for E, which is our z sub alpha over 2, times the square root of p hat times q hat over n, and we can solve this for n. So the first thing we're going to do is get rid of that z sub alpha over 2 by dividing both sides by it. And the algebra behind this should be somewhat familiar. It is very similar to what we did to come up with the error bound. The sample size given the error margin when we did the confidence intervals for the mean with large samples. A lot of the steps here are going to be very much the same. So our next step is to get rid of the square root, and we do that by squaring both sides. So we have now E over z sub alpha over 2 squared is equal to p hat times q hat over n. Now, we have a similar situation here to what we had when we did this in a couple lessons ago. To get n by itself, we actually have to flip both sides upside down. So if I flip this to put the z sub alpha over 2 in the top and the e in the bottom, and I also flip this side, then I'll be able to solve for n by simply multiplying both sides by both p hat and q hat. And I arrive at my final formula here. Now there's a couple of different ways to write this. Z sub alpha over 2 over E squared times p hat q hat equals n. Another common way this is written so that it can be, instead of having a fraction times the p hat and the q hat, sometimes it's written with, all into one big fraction. So in order to do that, what we could do is square the z sub alpha over 2 and square E separately. And then when we multiply by p hat and q hat, they just end up in the top of the fraction. So this is either form of these is a formula for finding the sample size for a specific margin of error. So we're going to go back to the student who was polling, the political science student who was polling other students to find out if they were registered voters. So the question here would be, how many students would need to be surveyed to be within, let's say, 2% of the true population proportion? Now let's keep the same confidence level. So once again, we have certain information here. We do not have n. That's what we're going to be looking for. But we do again have p hat. Excuse me. Oh, excuse me. Excuse me, very important thing here. We do not have p hat. And since we don't have it, we don't know what it, since, you know, in the original problem, p hat was 60% because of the 500 surveyed, we had 300 who were registered to vote. The problem here is we haven't surveyed anybody yet. We don't know how many to survey, and therefore we don't know how many we're going to get who are answering it. So the result for this, or the way that we deal with this, is we assume a 50-50 chance. And that's part of the thing here, is we don't actually know, until we actually know our sample size and go out and conduct the survey, we don't have any actual data to give us an estimate for p hat. Excuse me. So we're going to assume p hat is equal to 0.5. Now, I'll explain that in a moment as we move forward, but p hat being 0.5 means that q hat must also be 0.5. And the only other thing only other two things we need to make this formula go are the error margin, which we're given. We're told we want to be within 2%, excuse me, 0.02, 2% of the true proportion. And the other thing we need is the critical value. The critical value is a result of the confidence level. The confidence level is 0.90, which gives us an alpha of 0.1, an alpha over 2 of 0.05, and from the normal distribution we had earlier, z sub alpha over 2 then is going to be 1.645. The z-score is tied to the confidence level and nothing else. So if the confidence level is still 90%, then the z-score is still 1.645. And now we have all of the pieces we need. So n is going to be equal to 1.645 squared times 0.5 for p hat times 0.5 for q hat over 0.02 for E squared. Now, before I actually complete the calculation here, I want to explain why we're going to assume p hat to be 0.5. That's a bold assumption. We have absolutely no idea what p hat could be. Well, the idea is we would rather survey more people than we have to than survey too few. To make sure that we are to make sure that we're getting at least the right number of people surveyed, we want this product, this calculation to provide, we'd rather have it provide a bigger number than a smaller number. The bigger the number is, the more certain we can be of the accuracy. Of all of the assumed values that we could have for p hat and q hat, when we multiply them together, having both of them be 0.5 results in the largest product up there. For example, 0.5 times 0.5 is 0.25. If I assume p hat to be, say, 0.6 and q hat to be 0.4, then I actually get 0.24. If I assume p hat to be 0.9 and q hat to be 0.1, then I get 0.09. The idea is that if I assume p hat to be any value, and therefore q hat to be its complement, the bigger I choose p hat to be, or the smaller I choose p hat to be, the smaller this product will be. And if I make the product too small, it's going to result in a smaller value of n. And that could accidentally result in a sample size that's too small to give me the margin of error that I want. So the idea is that I assume p hat and q hat to give me the biggest possible product here, so that I get the biggest available sample size, because the bigger my sample size, the more confident I can be in my margin of error. So if that sounds particularly complicated, well, it is a little bit, but the idea is we'd rather go with a bigger sample size than a smaller sample size. So by using this particular combination of p hat and q hat, we are ensuring that our sample size is bigger rather than smaller. And from putting this in the calculator, it comes out to be 1,691.26 blah, blah, blah. And again, we always want to make sure we go bigger rather than smaller, so we're going to round it up. We need a sample size of at least 1,692 students to be within 2% of the true population proportion at the 90% confidence level.